disappear afterwards. Yeah, stay till gray.
Probably 1 minute break.
Okay. You got me frightened now.
Well, we'll see. Maybe you know. Your bound can be improved.
I don't know much.
Never mind.
Liz,
We are all
Hello.
Hello,
in your questionnaires that you have in your
Niels
packet.
Bohr, quantum mechanics. He said to us that the conference is a place strange which others not able to understand. That is what you present the first comments. And the second thing, my name is Uzi Svidensky and I'm interested in water lines and other domains. And as you may know, other lines of quantum fields.
I'm sorry, Mr. Wood, you're interested in what random
It's all, it's in all, it's 40 years old.
As the beginner, I know that's where I dropped out, right? The line number 4, right? Because I understand plus and minus, understand plus minus 1 to the power z. Gives measure, but what is the next step? There is a boundary. There is a
You have
boundary.
a probability theory, and then you calculate the average value. So you calculate average values.
There is
And these are called correlations.
Okay. You can specify boundary conditions.
One.
Then what, like, for my naive knowledge, like, this is descriptive. In PDS, you have boundary value problems. You have with the equation of minimization of functional, right?
No.
Forget about this, right?
Потому что ваш доклад не состоится, потому что
Start from final, then there is a boundary.
No, you have functions.
Chairman, обычно chairman, так сказать, двигает.
ну, не
Я
всякого
строже,
докладчика
я
можно
строже,
остановить.
чем он.
Не
Обычно.
всякого докладчика можно остановить.
Correlation.
Не,
You see, this,
ну это.
each sigma value plus or minus.
At least that.
Consider this to be a function of space.
So what is the unknown? I think every problem has a set
Yeah,
of
so,
knowns and set of
so
unknowns.
you can ask the question, what is the joint probability of all these sigmas? These are called correlation functions.
Yeah, you say you are the boss.
Okay, so we start again with Professor Bigonin from Irvine, California, who will talk about the slow light and frozen mode regime.
Yeah, I would like to thank the organizers for this wonderful conference and a chance to present our work on slow light. This is a joint work with Ilya Vitebsky, and in fact this particular project is a part of a bigger effort to use the ideas we came up with for some real applications like antennas. The slow light, I have to say a few words about slow light in a wider context. You should recognize that this is actually amazing that the light can be slow. In fact, the real light, as we know, is described by Maxwell equations in vacuum, and it propagates with one speed only, which is the speed of light. So how light can propagate slower? In fact, the light can propagate slower only by one means only, if it interacts with something, and this is coupled excitation. So light interacts with something. In our case, it will be with the with the actual medium, as described by classical Maxwell equations for 4 fields. You know, this is setting was clarified by Lorentz. This 4-field description of actually excitation of the electromagnetic excitation of the medium as it interacts with the pure light or pure electromagnetic excitation in vacuum. And this, because this other medium excitation can propagate at different speed, and because they're coupled, this is only how the light can be slow, can be slow. But in fact, we should realize that this, in fact, is the excitation where light is coupled to something, and this excitation propagates slower, or can propagate slower. And of course, you can come up with different mechanisms depending on this. And our particular realization of this slow light or slow propagation of light, which is essentially an excitation, more complex excitation, but as described by classical Maxwell equations in periodic dielectric structures, which are spatially dispersive. And in fact, so probably let me just go on with the next. So what are so-called photonic crystals? R is the word which described man-made periodic dielectric structures. They can be all the structures, of course, in 3 dimensions. This is real electromagnetic waves. But if the dielectric structure designed in layers like this, it's 1D periodic. And in fact, I will be focusing primarily on this medium, which is a layered medium, for several reasons. First of all, as we understood, one can realize a phenomenon in this relatively simple structure. And additional advantage for us that this analysis can be done analytically because the description of the eigenmodes or eigenfunctions of the corresponding medium is reducible via Flaquet theory to ODE's analysis. And so it can be done rigorously. So all the results I will describe are well written in several papers I'll tell, in which we have not formulated the statements as theorems, but they can be formulated as theorems. So we are interested, so in this talk I will be focusing on just 1D periodic structures. So it's really amazing. Once when I gave a talk on the subject, a physicist made a comment that it's amazing that still one can find something non-trivial in just layered structure. And so you may ask, so what can be non-trivial? So I can tell you in advance what is non-trivial here, because from a mathematical point of view, first of all, that the corresponding waves are really, it's a multi-dimensional field. It's actually 6-dimensional field, or at least 4-dimensional field under some circumstances. This is first. And second, non-trivial dispersion relations and anisotropy can really give some amazing phenomenon here, as I hope will show. So let me remind you how do we study the medium and its properties. So we can learn a lot by considering the structure of the eigenmodes. And also, after all, we study the propagation of wave packets. Now, when we're talking about slow light, so what actually is slow? When we're talking about slow, it means that we're talking about electromagnetic excitations, more precisely wave packets, which can propagate slowly. And a wave packet, as you know, is described, velocity of wave packet, or group velocity, is just the derivative of the dispersion relations. So one has to study, therefore, even the first step in studying wave packets is to study the eigenmodes and dispersion relations. So I remind you the basic things about the periodic medium. Probably most of the people in this audience know. I just fix notations. So we consider the eigenmodes, Flaquet, Bloch eigenmodes. Now the dispersion relation. So every eigenmode corresponds to a time harmonic excitation of the medium. So it's purely time harmonic. If you solve the equation, the solution is time harmonic with the frequency omega. And then one can construct a full set of eigenmodes, which are known as Flaquet-Bloch eigenmodes, which are described by or parameterized by quasi-momentum or wave vector, k. And for every k, there is an omega, and this is called dispersion relation. And so if one consider a homogeneous isotropic medium, the dispersion typical K omega diagram is this, as we will know. Now, if the medium is anisotropic, in fact, this is a degenerated diagram, and you can see if you make medium anisotropic, it splits in these 4 branches. In fact, actually, this is 2, 1 and 2. And if one imposes a periodicity in the medium, then dispersion relation develops so-called band structure, as described by Flaquet-Bloch theory. And in fact, under some designers we show, normally the dispersion relation is symmetric. Typically, omega of k equals omega minus k for almost all the medium, even magnetic. But an interesting phenomenon can occur, and in fact it can happen, that the dispersion relation can be asymmetric. And then this is actually one of the scenarios where one can get slow light. So, and I would like to emphasize a particular effort of this project was to come up with something which can be made from real materials. So we had to analyze everything, including losses and including how realistic are the parameters of the medium which we claim can give the phenomenon. And we did that. And my emphasis in this talk will be not as much on mathematical issues, which of course are there, and I will outline them, and they are well written in our papers, so I just refer for the details to the papers. But so I will emphasize on the phenomena itself and what are the parameters which provide for this phenomena. First of all, since our interpretation, and this is common interpretation of slow light, is slow propagation of, I will be precise, wave packets, then slow light means that there is a small group velocity, not to mention if one can manage to get 0 group velocity, this would be even greater. So group velocity is simply, as we know, gradient of the dispersion relation. And 0 is a derivative of dispersion relation. In fact, since we have a layered medium, we normally fix the angle of incidence, and then we have just one parameter k. So essentially in our problems it will be the derivative with respect to 1k. And for simplicity for this talk, I'll assume that the incidence will be direct, it's direct incidence. But interesting enough, if one consider oblique incidence, one can get even an edge in the design. And but I'll miss it. I will not discuss it in this talk, or will not emphasize at least. Now, from abstract point of view, if one has a dispersion relation, then if the obviously if the group velocity is 0, it's a so-called, as we know from elementary calculus, stationary points. So examples of stationary points which can occur in late medium are described or exhausted by these 3 situations. Delta omega is proportional to delta k squared at this special frequency where the derivative is 0, if such point exists. It can be proportional to delta k cubed and delta k to the power 4, and that's it. Why 4? You will see it's an elementary observation. You cannot have more than 4. So in late classical electromagnetic medium, the stationary points, in any case, no matter what the dispersion relation, just because of the underlying periodic dielectric layered medium, is described by these 3 possibilities.
Are you making a mathematical statement here? Or
Yes, it's a well, it's trivial mathematical statement, as you will see. That you cannot have more than 4 for electromagnetic medium, which is layered medium.
And are you looking at partial differential equation or ordinary?
The eigenmodes for layered medium, as I said in the beginning, are reduced to ODEs. Yeah, and it's essentially just things. General Flaquet-Bloch theory tells you that what structures they have, you fix K1 and K2, they become just parameters. For layered medium, everything is reduced. This is one of the reasons that we picked, not to mention its simplicity. And if we can realize as the phenomenon, in fact, there is an edge to do 3D structures. If I have time, I'll tell about that. But so far, this is just 4. You will see why. It follows from ODE, if you wish.
All the rigorous statements are about one-dimensional periodic structures.
Yes. Yeah. But, I know quite a few things one can do for 3D, but this is not the subject. Okay, so the first case is what is called regular band edge. If delta omega proportional to delta k squared, and when I say proportional, it means that coefficient is not 0. Then we have regular band edge. Then this situation is called stationary inflection point. And the third and the last possibility here is degenerate band edge, obviously. So these 3 possibilities exhaust what you can have in a layered medium. Okay, now an extra issue which we brought up when we started that project. So, okay, it's necessary, of course, to have slow light. You have to have, say, an infinite medium. If, say, the entire space is filled with your medium, slowly propagating wave packets. But this is not enough for any realistic device, because normally you have to couple that excitation with external, say, free space. And now, so the real problem is this. You have incident light, say, which falls on this interface between the medium and air. There will be a transmitted and reflected wave. It may happen, in fact, often what happens, that at these points, 100% of the energy is reflected. It means that you cannot excite these slow modes from outside. So this is an extremely important issue, because otherwise the only way to excite them from inside, it limits dramatically the amount of applications. So it's really an interesting issue. Is it possible, rigorously, clearly, to have a situation when finite fraction of the energy comes inside? And it turns out that in the case of stationary inflection point, it is exactly what is not only possible, in fact, I honestly say we have not formulated as the theorems because the papers published in physical journals, but they are essentially theorems. So, and I tell you, if I have time, how one can prove it, and we have an analysis which essentially proves it. So in the case of stationary inflection point, we have shown that the fraction of the energy which goes inside of the crystal at stationary inflection point, exact, or the reflection coefficient is strictly less than 1. Whereas for regular band edge or degenerate band edge, the reflection coefficient is exactly 1. So all the energy ideally is reflected by both regular band edge or degenerate band edge. But amazingly, for stationary inflection point, a finite fraction of energy always comes. And under proper design, you can make this fraction to be almost 100%. So you can have a situation which seems really strange, that the wave comes, almost nothing is reflected, it comes inside of the crystal. Now, in the stationary inflection point, not only the first derivative, which is group velocity, is 0, it's the second derivative is 0 as well. So you have a real and believable, strange propagation there, which is very non-conventional propagation. Because the ballistic propagation is velocity is 0, and its derivative is 0. So if pulse comes, and I'll show you, I don't know, maybe just I can interrupt a little and show you a little movie made by one of the collaborators, engineers collaborators. His name is Rob Lee. He took the structures we proposed and just made straightforward computation for it. It's one-dimensional structure. The accuracy is 50 digits. So you can really, if you believe that electromagnetic excitation is described by Maxwell equations, this movie, which I'll show you, shows exactly how pulse will propagate. This is, okay, this is the movie. Okay, so let me take my pointer. Okay, so let me run this movie. Okay, so this is pulse coming in the velocity of light. Here is the interface. You see, he did not optimize the structure. 50% of the energy reflected, but 50, not 100. And 50 comes in, and you see this pulse. This is it's real pulse, how it propagates inside of the medium. You remember probably the velocity, which was, of course, everything is slowed down so you can see. But the initial pulse, what is the speed of light? So you see, this is real picture. What is going on with the real pulse, including the distortion?
What is the meaning of this little hole?
What is what?
Why there is a white thing under the?
It's artifact. It's probably something dense and just. See, it deteriorates now. It propagates here. It's real finite slab. Okay, so it's reflected back, and you cannot see it because it's instantaneous. And now another, the same pulse is reflected and again propagates in a slow mode regime. But of course it's now, it's finite bandwidth, so it has to disperse sooner or later, and it does. But amazingly, and they first observed it experimentally and when explained it, the shape of the pulse is kept, good, and some other things come very good, so which is of course very good for applications because the group velocity is identically zero, only this is real pulse, so it has finite bandwidth. So the group velocity is 0 for single frequency, but then you build a wave packet monochromatic enough, so it should, has reasonable bandwidth, so there is a pulse. And in fact, this is a very robust phenomenon. So I'll tell, it's so robust that even amazingly, unexpectedly, even losses, if you know the numbers, it actually the phenomenon is impossible to see for really huge losses like 10 minus 2. For 10 minus 3, the losses are still visible. Not the losses, the phenomenon. For 10 minus 4, it's almost like ideal. So it's really very reasonable. It's really very robust phenomenon, including the losses.
That theorem is saying that for stationary inflection.
Because I'm a mathematician, I respect the word theorem. I mentioned 3 times already. We have not formulated statements as theorem, but they can be formulated as theorems.
If they were, that would have been about a stationary inflection point with reflection coefficient less than 1 and identically 0 group velocity.
No, group velocity is 0. It's easy. It's by the definition. So we assume that there is such a point. Now, the next issue would be, okay, on the paper, how does a material exist where you can have this? And I'll show you it does. It requires some complexity, complex enough design, but not too complex, but not too simple either. If it's too simple, it cannot work. So the precise statement would be that, there are dielectric media, a potential theorem, and not just one, many, for which there is stationary inflection point, and we describe class of this media, for which such a point exists. We explain how to achieve it, because it's normally, of course, never in practice you have it. So you have to have some tunability. You have to say what should you vary in order to get there. And in fact, because you have normally the bandwidth where this phenomenon is sound is wide enough, it's not just one frequency. So of course, ideally, but ideal statement theorem would be that the reflection coefficient, as you said, is strictly less than 1. And this, not formulated as a theorem, this statement is there. I explain what this real mathematics is about. If you have such a phenomenon, what is mathematics there? This would be a legitimate question. And I'll indicate where the mathematics phenomena comes into the analysis here. Okay, now this is a very basic analysis, and I want to make a few points here. So now I analyze this in fact, as you know, the reflection of the wave is pretty subtle and hard to catch. Now, if you describe something in abstract terms, like you have a dispersion relation, and it's implicit, even I know that the medium is layered, it's an implicit description. So the very fact that one can analyze based on the assumption that if you have that point, then the reflection coefficient is strictly less than 1 is quite amazing. But this, in fact, can be done. The input of the layered medium is here. So, first of all, this is the basic, common knowledge about, any electromagnetic waves propagation. So you have an incident wave, and there is a conservation of law of the energy flux. The transmitted flux, what is called equals the initial plus reflected, and the transmission coefficient is the ratio of S to SI. I'm sorry, incident. So this is what is incident, this is transmitted, this is reflected. So tau shows the transmission coefficient, this is its definition. Now I remind you that fluxes are defined via, like in field theory, via the, like Satin von Noether, the equation which describes within the classical energy conservation law in a medium. So it has flux. It's the.
Have you got the T and the I the wrong way round up there?
What?
The incident is equal to the transmission plus reflection, yeah?
Yeah, but it's algebraic sum. The sum is algebraic.
This is a sign convention. You have made a certain sign convention.
Yes, you've got
No, the signs are designed, of course, it's algebraic sum. So you properly said the signs. Yeah, but it's we write which is conventionally people write, so we did not want to upset. So I would probably also, this is not, it's not positive numbers, they can be negative. Okay, now this is very important relation. Look, that a quantity like flux of energy and the density of energy is related to the setting of the field theory. Now, group velocity is a quantity related to a wave packet. So here is an interesting relation for eigenmodes only. In fact, for periodic medium, this flux and this energy, in fact, are averaged densities over the Selov period. In general, it should be volume average, but in the periodic medium, they are reduced to the average. So this, I have not seen this formulated as a theorem, but in several books, this is fundamental relation, as a very general relation is analyzed, and I can give you references in particular in the book by Witham on waves, and there is another book by Ostrovsky and Potapov, very nice book on waves. This is two references where this situation analyzed in general. Whether it meets our standard of the theorem, I would say no. But this would be something interesting to establish. I checked that how one can establish this for the medium like we have, and mathematics is reduced to a simple analysis will reduce to a simple problem, which you all know. If you have a self-adjoint operator which depends on the parameter, and lambda alpha its eigenvalue, that its derivative equals to this. Using that theorem, one can establish this relation cleanly for the layered medium. And in fact, so here is the elementary analysis. Now if you look here, flux equals the energy times group velocity. If the group velocity is 0, or approaches 0, say we come close to that point, and W, the density, say is bounded, then obviously the flux will be 0. And therefore the transmitted energy will be 0. Now, so the only possibility that the flux is not 0, that W must grow. The average density must grow. And everything is normalized by the conditions that incident flux is 1. Because as you know, eigenmodes are defined up to constant, so it's meaningless to say whether energy is big or small unless there is some clear way to normalize them. So if everything is, and this is for semi-crystal, everything is normalized by a condition that incident energy is, say, normalized by 1. It's 1. So this must be a condition. In fact, if you wish, the rigorous proof, or it's something which is close to this, goes in a different direction. Actually, we show that the flux is constant, non-zero. And via this, we show that W approaches infinity. The rigorous proof actually establishes directly that the flux is not zero. And then it implies that the density of energy will then grow, which means, which is not surprising, if the wave comes and does not propagate, it compresses and the energy must grow. That is just by conservation of the energy. Okay, so let me give you the bottom line analysis for the band H, which includes this reflection and everything. So this is what happens for a regular band H. For regular band H, delta omega equals delta k squared up to a constant. The group velocity, if we get close, vanishes at the rate square root of delta omega. In fact, for the regular band H, the density of the energy remains finite. It's a fact. It does not grow. And consequently, the flux approaches 0, which means that the reflection is 100%. Ideally, at this very point, the reflection is 100%. Now, stationary frozen mode regime, I will explain in more detail. Frozen mode regime is about mode now. So I'll tell what is this. And stationary inflection points, the situation is qualitatively different. So here, delta omega is delta k cubed. Now, group velocity vanishes at the rate delta omega to 2/3. The density of energy grows to infinity at the rate delta omega to exactly minus 2/3, and the product is finite. But as I said, in fact, the rigorous proof goes that you show that S is finite, and via this, we get this. Okay, now I show you how the energy density behaves inside of the crystal when you approach the special point. So ideally, at stationary inflection point, what is frozen mode, it's a true Flaquet mode, which is not Bloch mode. It's not just oscillatory mode. It has linear component. As a derivative, it roughly, it behaves as or x squared even, as you know. So ideally, this is a profile of the eigenmode inside of the crystal. Here you don't even see it, the incident, So this is the energy density square of the amplitude of the field for this mode inside of the crystal. Outside it is 1. It's so small you even don't see it. Now it grows like this without any bound. So this is Flaquet mode, true Flaquet non-trivial mode. Now, if we are close to this situation, but not yet there, so suppose that we have this frequency, we come to this frequency from the left to right. So if the frequency a little bit less, so first it resembles the real Flaquet mode, but then it reaches, saturates, and then it goes like this. Now, if you get closer, it has roughly the same shape, but this distance for which it resembles true Flaquet mode is larger. And ideally, it becomes this, and then when you pass it, it's about the same shape. So this is a typical shape, a bump like this, then it goes a little well, and then it flattens.
Could you elaborate, please?
Uh-huh.
You're talking about true Flaquet mode, which is actually x times.
No, obviously, you have degeneration of the spectrum. This is expected.
You are in one-dimensional situation.
Yeah.
So what kind of degeneration are we talking about? Why?
Your omega, when you...
Why the stationary inflection point is associated with...
Okay.
This means that
Okay.
another band is...
Okay, I'm explaining you, and this is how it was you may view it as a computer-assisted proof. So how did we prove that there is a medium for which it exists, in particular that there is degeneration? The stationary inflection point. The stationary inflection point. So if you have a medium, you can have a dispersion relation like this with these three real roots. If you start to vary the medium parameters, at some point it becomes like this. So somewhere in between, these three roots merge in one. And this is how you get it. And I'll show you another, of course, there is clear mathematical manifestation, there is degeneration. I'll come to this. By the way, but this is really how we proved that this is possible. How you can prove that this is something exactly possible. We proved it because this is such a simple medium. You can do computation with the accuracy 50 digits using Maple for concrete medium. So we show for some parameters you have this. For some parameters you have this. So somewhere in between, by continuity, you have to have exactly stationary inflection.
So it's an ODE but not Hill separate.
Huh?
What you're saying, it's an ODE but it's not Hill separate.
I'll tell exactly what it is. It's a transfer matrix. You formulate the equations via transfer matrix, and no, I'll tell about this.
What is the physical meaning of these tuning parameters which you...
Oh, width of your layers. Width of your layers.
Not more?
No, you can use more. You can use a magnetic field to change the, say, mu. But when I'll explain you what the medium is, you will see the electric field can vary the anisotropy to some extent and some other parameters. One of these parameters which one can vary is the width. But of course, when you make something real, you want to have something which better than width, because when you make it, you cannot vary it. But in essence, in fact, you may, because some layers can be air, and you can just have like an accordion, and in fact, you can move. It depends, which device you want. But also, you can tune it electronically by changing external fields.
In contrast to this standard edge effect.
No, band edge, I'll tell you, you have to have certain design to have stationary inflection point.
Here there's always a single band, right? And inside the band, no edge.
What do you mean single band?
I mean, it is all happening. One single band, right?
Yeah, as I said, you will see the analysis. You can have your dispersion relation allows for every frequency exactly 4 Ks. So the number of real roots cannot be more than 4. And you will see obviously why. And then with this constraint and everything, you get this. Now degenerate band edge is this situation. It's somewhere in between. Namely, group velocity vanishes at high rate, delta omega to 3/4, but the density of energy explodes at the rate only delta omega to minus 1/2. So ideally, the flux vanishes too, and ideally there will be full reflection. But the degenerate band edge is really nice structure, and it has its own advantages, I'll show you, especially for finite slabs. In finite slabs, you can have some new interesting phenomena. Okay, this is the, you can see how profile of eigenmodes for different omega. So here we go from the band to the degenerate band edge and then to the gap. So we're in the band close to the edge. This is, it looks a bit different than stationary inflection point, but pretty much, similar. This is ideal degenerate band edge, and then of course it must decay when you go in the gap. Okay. So this is the bottom line analysis. Actually, I already told you, degenerate band edge reflects everything. Stationary inflection point, if any, is really a nice option if one wants to have something which is ideally not reflective and slows down dramatically. Degenerate band edge slows down more, but ideally it reflects everything. But there is some peculiarity there that, the pulse can come, stay, and then comes out. And this is what happens, because the degenerate band edge structures in many ways are very nice. So,
May I ask
yeah.
about this reflection?
reflection I have, I'm apparently missing something. Your calculation with this, like pointing vector or whatever, you do showing that you have reflection. What do you mean reflection? You have semi-infinite periodic medium, and the wave comes from the air.
Exactly.
But it doesn't seem that you use the fact that it comes from the air. So why cannot you?
It does. It does. It does.
In both directions, it should go through.
It does.
So
First of all, for station inflection point, the dispersion relation is asymmetric. In late medium, in order to get station inflection point, you have to have a magnetic component in your dispersion.
This is not what I am asking. I am asking the following. Imagine that on the left, where the wave comes from, you have continuation of the same periodic waveguide rather than air. Then there would be any reflection. This wave would go through.
I'm not sure I understand. You have semi-infinite structure,
But
ideally semi.
imagine that you have full infinite structure, cut it into half.
Yeah.
And then your wave goes through nicely, it's infinite periodic medium, but where does your proof that it doesn't that it reflects from the boundary? It doesn't work for the fictitious boundary in the middle of periodic.
Because this is it's not real boundary, it's not really different medium. You have semi-infinite structure air in your crystal. You have incident wave, reflected wave, and transmitted wave.
Okay, maybe.
I don't know what's.
Are you trying to say that the structure of Laquet solutions, the one that you showed to us, is valid only for the semi-infinite structure?
Of course not. No. But you have to glue them properly. You have to glue them properly on the interface. And this is where this miracle occurs. So here is now you can see explicitly the eigenmodes. You fix K1, K2, the angle of incidence. Then they become just like parameters of the medium. And then you get the following equation which describes the profile of the eigenmode. And if the incidence is direct, then K1, K2 equals 0. So ultimately, when you take into account the divergence free condition, you get four-dimensional field. Where this number 4 comes. Okay, then you do the some generic Flaquet-Bloch analysis here in terms of the relation between frequencies and wave numbers. And by the way, in semi-infinite crystal, you have to introduce so-called evanescent mode with complex case, which do not appear in spectral analysis in infinite medium, as well known. But they naturally appear when you have semi-infinite crystal. You have to introduce modes which are called evanescent, which actually grow exponentially in one direction, in order to describe the situation when air is coupled with the crystal, which is non-existent if you have the infinite crystal. These modes are not there. And here they will play extremely important role. This is evanescent modes, which allow you to glue inside with outside. Without evanescent modes, this would be impossible, but this would mean that there is a contradiction in mathematics. There is no contradiction because you have to introduce so-called evanescent mode with imaginary case, actually complex valued case. Now, the eigenmodes are described, as well known in the Fallette medium, via transfer matrix, which has some fundamental properties. Now, transfer matrix is 4 by 4. It is allowed to depend on the frequency because the medium can be lossy and dispersive. Now, the spectral parameter zeta, its meaning is actually e to ikl. L is a period, k is a wave number. So you get an algebraic equation with coefficients which depends on frequencies. This is how it really, for real medium, how you do it. So you find k as a function of omega, not vice versa. Okay? Now you may say, what miraculous happens that you have this stationary point? So what happens at the stationary points? At the stationary points, your transfer matrix gets non-trivial Jordan structure. If you have one of the stationary points for, say, let me see, regular structure, if you have arbitrary omega, the matrix is diagonalizable. Okay? Now, for regular BNH, for regular BNH, it develops 2 by 2 Jordan block. Okay? So this is where you have degeneracy, you see? But this is not just degeneracy, this is Jordan block. No, as you know better than me, this is how you get Flaquet modes. You get Jordan block instead of diagonalizable. By the way, funny, maybe Uzi is different. Just few physicists I met know that not every matrix is diagonalizable. Did you know?
Thank you.
Well, but I'm serious. They just believe that every matrix is diagonalizable. When I showed them simple matrix 0, 0, 0, 1 square equals 0, they were stunned. Okay. So stationary inflection point correspond to the Jordan block of the rank 3. A degenerate band H point correspond to the Jordan block of the maximum possible rank 4. And this is how you get immediately Flaquet modes. Genuine Flaquet modes, and this is the kind of degeneracy you get here. Is this, does it answer the question now or not? Is this degeneracy? This is how you get Flaquet modes. Of course, you can do it also straightforwardly, as we did in our paper for physicists, by differentiation the eigenmode equation and taking into account that d omega over dk equals 0. When you differentiate, you see that you get an extra x. It's not a Bloch mode. You show that the derivative of your mode with respect to k is also an eigenmode, and obviously, even if it was a Bloch mode from the beginning, the derivative is not a Bloch mode anymore. Because you have ekx, when you differentiate, you get an x.
But that's basic Bloch theory.
Huh?
That's what basic Bloch theory says.
Yeah, but I think it's even more sound to see really you have a really Jordan block. Okay, as I said, when you analyze, complete analysis of semi-infinite structure requires introduction of what is called in physics evanescent modes, and require you to introduce in otherwise infinite medium modes which are not needed by the spectral theory of the infinite medium. You don't have exponentially growing modes as legitimate modes there, but because you have semi-crystal, they play a role in semi-crystal because the part which grows is cut at the interface. And so what happens, a new phenomenon, what happens when you have now the whole analysis now is reduced to spectral analysis of perturbation of the Jordan block. The spectral theory, what happens if you perturb Jordan block? In general, you get Posel series kind of things, but we had to do by ourselves complete analysis for the 3 and 4 matrices because we found it nowhere. The complete analysis, including formulas of the perturbation and all these things we did on our own. It's in our large paper on the waves in random media, where we did a survey on the photonic crystals and slow light there. Now, this is concrete structures for which you can have stationary inflection point. The concrete structure for which you can have stationary inflection point, the period must have at least 3 different layers. 2 are not enough. For 2 layers, you can show there is always a point of symmetry, and it guarantees that the spectrum will be symmetric. So now, it's clear that in the case of layered medium, because the number of roots is 4, that to get stationary inflection point, you must have a symmetric dispersion relation. Because if it is symmetric, you have stationary point here, then symmetrically you have another stationary point. Stationary point carries 3 roots, then total number of roots then 6 instead of 4. So it's impossible. So the only possibility for the layered medium to develop a stationary inflection point is to be asymmetric. So here, in order to get it, you have to have here this A1, A2, and F stands for the anisotropic, must be a layer with non-trivial anisotropy, another also anisotropic, but Say if it's isotropic, it must be rotated with respect to this, and this must be a magnetic layer. Now here is the corresponding tensors of epsilon and mu, for which you can get it. So this is actual design of the structure which can have station inflection point, for which we have shown that it does. Now, anisotropic structures at microwave frequency range are, pretty common, but you can find them. But at light frequencies, anisotropy is small. So the question is how you can get anisotropy. One way to get it, and today it's possible and people do it, is to make it artificial isotropic medium by making this design at the wavelengths which substantially less than the wavelengths of your light. So nanotechnology allows to design structure like that which will be anisotropic. Okay, now this is a frozen mode regime is related to this state when it described its non-trivial Flaquet mode. And if you take a finite slab, you can see it, you can enhance the phenomenon putting a mirror at the end instead of, say, free propagation. So now if I have a little time, I have 5 minutes. Well, I had some transparencies to show you. For finite structures, there is a well-known phenomenon which is called Fabry-Perot resonances. Of course, they occur here, and there are some peculiar interesting phenomena occur for the finite structures in the regime of degenerate Banach. Now, advantage of degenerate Banach is that you don't need to get it. You don't need magnetic material. Magnetic materials are often very lossy. Though we discovered the losses, in fact, the phenomenon is pretty tolerable to losses. And there is another interesting subject which I just can mention. I cannot time to speculate much. That in fact, for composite structure, if you increase losses in one component, miraculously, for most of the frequencies, the losses makes losses lesser for the entire structure or for most of the frequencies. And this I talk to people, they know about this phenomenon. And it has a really nice, I can show you this phenomenon for 2 oscillators after the talk if you wish. So for composite medium, you take one component and make it very lossy. You may expect, well, that at all frequencies everything will be lossy. No, it's less lossy for most of the frequencies. This is non-trivial effect of the multi-component structure. And people who know composite materials know that miracles like this can happen. So this is the resonances one can observe. So what I want to say is the last statement about applications, that in fact degenerate Banach allows to make structure if say one needs all the phenomena. If you use regular Banach, when you design say cavity, the quality is proportional to n squared. For the degenerate Banach it is n to the power 4. Therefore you can design a structure which is like square root times of the, so it's much smaller and has the same performance for degenerate Banach versus regular Banach. And degenerate Banach does not require magnetic structure, and it can be realized for real light. Okay. Thank you.
Can I ask you 2 questions, please? One, when you have an interface, you are dealing with 3-dimensional situation, you have also what is called the surface waves. They are associated with the evanescent modes in the perpendicular direction, but a part of the intensity can go into them. Now, in your analysis, I didn't see this coming about.
Now, first of all, when I talk about group velocity, it was a group velocity in this direction. If you have incident, your wave, though it slows down in this direction, it can still shift parallel to the surface. And in fact, you can have here what we call...
The intensity relations that you have must include also that part into account.
No, of course. Without this, no way you can make an eigenmode. You have to have evanescent modes, otherwise you cannot glue and make a real perfect eigenmode.
So when you have an intensity, so the incoming intensity is is equal to the sum of the penetrating, so the transmitted, reflected,
Yeah, but
and also along the.
no, it's not. It's because this is vectors. It's not just you don't sum up, absolute values.
So this was
This is the key, because when you have Jordan block, when you come close to it, the eigenvectors almost merge. And they actually merge, and Jordan block, as you know, has a single eigenvector.
Not every matrix can be diagonalized.
This is why.
When you show this the periodic three component, I had a question. Suppose that you take a Penrose tiling. Will that act in a similar way? And
I guess if you
see you can propagate. Penrose tiling you can see. You can have the crystallographic structure.
Yeah.
For all the analysis is very similar.
I think that first of all, wisdom you can get here. It's interesting the role anisotropy via vectors. Without anisotropy, you would not have it. It's amazing. I still don't have hand wave explanation how you get it. I have explanations via Lagrangian, gyroscopy, but I would not call it hand wave. Now, in 3D crystal, it's by its nature, it's anisotropic. So it has already built-in anisotropy. And I believe that in a 3D photonic crystal, you have lots of the slow modes. And, this is a different study. I did not do it, so I can only speculate.
It's very easy.
But I think,
it's actually
of course.
in dimension higher than one.
Of course, in three-dimensional case, I believe that you here for late medium, you have to have magnetic material in order to get stationary inflection point, because of the prohibition. You have 4 roots. If you have stationary inflection point, if the symmetric relation would give another 3, you have 6 when you have 4, so it's possible. You have to have asymmetry as a must in order to get stationary. If you have more complex structure, you can have stationary inflection point without that constraint, without magnetic material, which are very, have a peculiar behavior and harder to analyze. There are some advantages to use them if you know how, and it's the engineers, they don't trust any abstract mathematics, even analytic. So they did explicit calculations because we produce concrete structure, and there are many people who can compute it. So regardless of whether they understand or not the analytical, this Jordan block business. Yes?
If I understood you correctly, you reduced it to a one-dimensional problem since you hit the surface perpendicular.
No. You reduce it to one dimension, not we reduce it. Everybody who knows this business, it's not our discovery.
Yeah, I'm just saying, I just wanted to explain. So the technique you use is the transfer matrix.
Yeah, I explain in one.
Is there something, a replacement if you are not in this one-dimensional?
Of course not. No. Transfer matrix is inherently one-dimensional, and it describes the structure of the eigenmodes. This is what it shows.
What replaces it?
You have to do totally different analysis. There is no substitute. The transfer matrix, there are, as Peter said, there are some slow modes by the obvious other mechanism, and you have just to study them.
You still have a layered structure, I guess that was your question. A layered structure, but not orthogonal.
If you have layered structure, this is one. If you have layered structure, okay, then.
Yeah. Then you are still okay, I guess, right?
Oh, he doesn't have transfer matrix.
Then your.
It's one-dimensional.
The eigenmodes, Robert, the eigenmodes for the layered medium are periodic, non-trivial, only in one variable. This is why you can get rid of 2 variables and get ODE. And this is why you can do a relatively, by mathematical standards, simplistic analysis. Okay? Okay.
You say there's no replacement.
This is right for this case.